Hello everyone. In this video, I will try to make a whole 6502 based computer on just a single breadboard. This is a 6507 microprocessor. It's a 6502 core in a 28-pin package instead of the usual 40-pin package. Even though it looks different, it'll run the same code. Because of the missing pins though, it can only address 8K of address space instead of the 64K of the 6502, and it's missing a few things, like the interrupt request line. When I come across these chips made by Rockwell, I can't help thinking about Close Encounters of the Third Kind and the end scene where the extras are wearing white jumpsuits with the Rockwell logo on the back. I guess Spielberg thought that obviously the big government contractors must be in on covering it up if aliens arrive. Or maybe the movie was hinting that that's where Rockwell got their tech. Aliens. Just like in the Transformer movies. Wait, no, that's not what this video is about, and Rockwell definitely got their tech from MOS technology. Let's get back to the 6507. When it was released in the mid-70s, the biggest selling point was the lower price because of the smaller package, and of course that it's physically smaller, also taking up less of the expensive PCB space. But why am I talking about a 47-year-old CPU design at all, you might ask? Well, making 6502-based computers like the good people over at 6502.org do can be a lot of fun, but like we see in Beniter's videos, for example, also quite an undertaking, or at least a long weekend project. I thought it would be fun to simplify that and make a more compact version. Beniter uses a design by Garth Wilson that has a 40-pin 6502, a 40-pin 6522, a 28-pin ROM, a 28-pin RAM chip, and a 14-pin NAND. That's already 75 pins wide on a breadboard. Not to mention the crystal oscillator can he uses is 14 pins, and we also need LEDs and buttons. And a full-size breadboard is only 63 pins wide. There's just no way we can fit all of this onto a single breadboard. At least not without making some compromises. But maybe we can still do it. Let's get back to the 6507 once again. If we use that instead of the 6502, we can save 6 pins width, but we're still nowhere near the goal of making everything fit on a single 63-pin wide breadboard. Of course, we can technically get it running and blink some faint LEDs with the address lines and a ROM full of code and an oscillator, but while that would certainly fit on a breadboard, without at least a little bit of RAM and I/O, there's not much that our single breadboard computer can actually do like this. And if you pulled the RAM from any modern computer, it wouldn't even power up, so I think we need a bit more to call it a computer. Besides the ROM and RAM, we also need a way to communicate with the outside world. At the very least, blink an LED and read a button, the most basic input-output. For the I/O and RAM, luckily we'll find the compromise I hinted at earlier that might just make this project possible. Instead of using a 40-pin I/O chip and a 28-pin SRAM chip, we can use a single IC that combines both, at the expense of the amount of RAM. If you've seen my previous video on that, you'll already know what I'm talking about, the 6532 Riot. It has the same amount of I/O pins as the 6522 VIA and also has a timer. But most importantly, it has a little bit of RAM, just enough to make a working computer. And even better, we can skip the 28-pin RAM chip. Of course, we also need a bit of address decoding, and I decided to go with a hex inverter for reasons I'll get into later. That actually looks like it might fit, so let's try it out on a breadboard. Now, all we need is power, some kind of clock input, and some software. So let's get started. I like to start out by connecting power and ground on each IC, and after that we can move on to some more interesting things. Even if I'm just fiddling around with a breadboard, I like to throw what I'm doing in a KiCad schematic to make it harder to accidentally roast the ICs. At the very least, it helps to keep track of where the wires are supposed to go. It also makes it easier to share, so of course you'll also find this project on my GitHub repo. The link is in the description. Initially, I planned to use an inverter crystal oscillator instead of the CAN oscillator, so I left both in the schematic. I decided to use a hex inverter IC for the address decoding instead of an NAND gate IC because I assume it's a bit more predictable in the gate delay and hence the frequency if we try to make an RC oscillator without a crystal later on. Also, even if we use 3 inverters for the oscillator and 1 for the address decoding, we still have 2 inverter gates left over that we wouldn't have with the NAND gates. But of course, a NAND IC would probably work fine for the oscillator as well. If you'd like some hints on how to make an RC oscillator instead of using a crystal, I suggest you check out Fairchild App Note 118. I'll try to breadboard this well enough that we can see where most wires go. It takes some time to trim the wires and find the best order for the chips, but it makes troubleshooting so much easier when you can actually see how things are hooked up. On pin 1 of the 6507, we have the reset line that'll need a pull-up resistor. So will the ready line on pin 3. I'll also hook up the reset line to a push button with 2 of the legs broken off to make it fit, since we don't really have a lot of space left over. It just has a 100 nanofarad capacitor and the pull-up resistor for debouncing. That's not perfect, but it'll do. I also like to add some bulk capacitance on the breadboard power rail and a 100 nanofarad capacitor per IC, as close to the power pin as possible. I also like a visual indicator that power is connected, so I just add an LED with a resistor on the ROM power line. It's very faint on camera, but it's going to be okay in real life. After that, we can move on to the data and address buses. First, I'll hook up the data bus to the riot chip, and after that, I'll hook it up to the ROM. While I hook those up, I'd like to talk a bit about what happens when the 6507 resets. Since the 6507 only has 8K of address space, it might be a bit confusing to think about the normal 6502 reset and interrupt vectors at FFFA to F. Since the 6507 only has 13 address lines, it can only really address the address range of 0 to 1 FFF. And you might think that it has no way of addressing the 6502 reset vector and must have its own special reset vector. But I guess you can say the 6507 doesn't really know that. The CPU just sets the address lines it does have to what they would be for the reset vector, and it's up to the designer, that would be us, to make sure the ROM outputs the right data. You can imagine it like the 6507 actually does have the address lines internally, but they're not connected to anything, so it doesn't matter if the address is 1FFF, 7FFF, or FFFF. Our address decoding must output the same data either way. And speaking of address decoding, since I use a 64K ROM here and we can only address 4K of that, I simply connect A12 to 15 to the ground rail. After that, it's time to hook up the rest of the address lines to the 6507. Since we don't mind the ROM being active all the time, as long as it only outputs when it's being addressed, we can connect the chip enable to ground. How we hook up the address lines of the riot depends a bit on how we want to organize the memory map. I decided to put the RAM part first from 0 to 7F by connecting the RAM select line directly to A7. If instead I had run it through one of the leftover inverter gates, I could have put RAM at address 82FF and control registers from address 0. Another common way to do it was to hook up RAM select to A9, which meant the RAM would repeat from address 0 up to address 1FF. That way, all of 0 page and stack space had RAM in it, mirrored of course, and the riot registers were accessible from address 200. But for now, let's share 0 page between riot registers and RAM. Faster I/O is another advantage of doing it this way. We don't really need the CS1 line of the riot, so for now we can simply connect it to 5 volts. It's starting to get a bit crowded around the A12 line of the 6507, so I'll connect the inverter we'll use to output enable the ROM to CS2 on the riot. It's always a good idea to make sure logic gate inputs have defined states, since they might start oscillating or draw extra power, or worse if they don't, so I'll connect the unused inputs to ground. Now all that's left is to hook up the clock input and the read-write line for the riot. With our computer hardware mostly finished, I guess we're ready to write some code and maybe blink an LED. So let's grab the ROM and see what we can come up with. I've cheated a bit ahead of time and written the part we need to blink an LED using the riot timer and I/O. I like to use the CC65 compiler for 6502 assembly because it's easy to work with, and if I ever need it, I've heard the C compiler is pretty good. For this project, I think we'll be fine with a bit of assembly. Don't be confused that I wrote out every single register of the riot. It's not in any way necessary since most of it isn't used in the code below, but since the riot has a funky control handling, I'd like to take a minute to explain it. Usually a chip with special features like timers and interrupt settings would either have dedicated pins to indicate a control command or a register at a specific address that sets these features. The 6532 riot, on the other hand, controls interrupt activation, edge polarity, and timer prescaling in a pretty peculiar way that we need to understand if we want to blink our LED. Instead of a control register like the data direction registers for the I/O ports, the riot determines the features you want by the address you write to, or even just read from in some cases. The first example of this we already see at address 4. If we simply read it to get the current timer count, we also disable the timer interrupt request, which means we will never get an interrupt from the timer. But what if we want to be able to read the timer and still get an interrupt? Well, we have to read from a completely different address. For the riot timer, the address bit used to enable interrupts is the high bit of the lower nibble. Said another way, we need to read the timer from address 0C instead of 4 if we want to read it without disabling interrupts. I'll skip talking about how PA7 edge detection control is set since we won't be using it, but as you can see, it's the same idea. Different addresses control which features we get. The same goes for configuring the timer that we need to blink our LED. Depending which address we write, we get a different prescaler of either 1864 or 1024. With that in mind, we can start looking at some actual code. When I reset a 6502-based system, I always like to make sure it's not in decimal mode, interrupts are disabled, the stack pointer is something predictable, and RAM is cleared. We won't actually need any of that just to blink an LED, but considering we don't have enough RAM installed to cover the whole stack space from address 100 to 1FF, we'd probably get in trouble as soon as we try writing our first subroutine. By setting the stack pointer to 7F, we let the stack grow downwards from the top of RAM and put our variables at the beginning of RAM. To blink an LED, we need to set the pins to outputs by writing a 1 to the corresponding bit of the data direction register. I'll just set the whole port to output by writing FF to DDRB. The reason I set the whole port is because I can use the increment instruction as a trick to make all 8 pins of the port count upwards in binary, at different rates of course. That makes it super easy to spot mistakes simply by moving the LED. Even though controlling the riot might seem funky, it's actually quite easy to use the timer. By writing 244 to the timer at the address for divide by 1024, the timer should run out in about a quarter of a second. Since we don't need to do anything else while blinking our LED, we can simply read the timer until it runs out, and when it reaches 0, jump back to the beginning to flip our LED on PP0 by incrementing the port. As you can see at the bottom here, I still let the 6507 believe it's accessing vectors at FFFA, even though that is technically a mirror address. Let's put this on our ROM and see if it works. First, I like to hook up a resistor for the LED and then the LED itself. Sadly though, it doesn't work. The power LED is on, but that's it. Sometimes things just don't go according to plan. So even though I fixed this later, I decided to leave this part in, since there's no guarantee you won't run into at least one of the problems I test here if you try this at home. I noticed that when I burned the ROM, I didn't actually get a verification OK message. And sometimes things work fine anyway, but since it didn't, I wanted to make sure the ROM was good. Since a good ROM didn't change anything, I gave the board a quick look for loose connections, but still having no luck, I decided to use the frequency feature on my multimeter. First, I checked the input frequency from the CAN crystal is good, and afterwards I checked that the 6507 is also outputting Phi2 on pin 28, since that's a convenient indicator that the chip isn't completely dead. Since it wasn't completely dead, I thought I'd check if the reset sequence was happening by checking the top address lines. That should go high when accessing the reset vector at FFFC. Since A12 didn't seem to change at all, no matter how many times I hit the reset button, but simply stayed at ground level, I had reason to assume that the 6507 had one or more bad pins. Luckily, I have another 6507, and after popping that in and connecting power, the LED sprung to life, even without touching the reset button. We have a working single breadboard computer. I think this is the first and only time it was actually a faulty component that was the problem and not something I did wrong. I think it was Don Lancaster who said to always blame yourself first and the components last when your new creation doesn't work, since it's usually something miswired or misunderstood. While that is rock solid advice that I will keep forever, this time it turned out to be a single fried address pin. When working with these old ICs, I guess the best approach is to blame yourself first, but still make sure you have a spare available. With the LED working, I just have one more thing I want to do before calling it a day. While a single blinking LED is pretty, what we've made here is basically a complicated 555 timer circuit. So to really call it a computer on a single breadboard, I'd also like it to act in response to our input. While I could probably get it to run BASIC like I did with its 6502 big brother, maybe with a few things shaven off, or maybe get it to run code delivered by a 2.4 GHz wireless module, I'll settle for something simpler and just get it to respond to a button press. Not as impressive, but it'll get the job done. The button will need a pull-up and a capacitor for debouncing if I don't want to do it in software. Instead of connecting the button to PA0 like I did in the schematic, I'll hook it up to PA7, so I can just use the bit instruction to check for button presses. Let's see if we can adapt our code to also accept input. Since the riot resets to making both ports inputs, we don't need to write anything to DDR-A. All we need is for the button to change what our computer does slightly, so we can keep the timer value but just change the prescaler by writing to a different address. That should make it blink visibly faster. The bit instruction will put the state of PA7 into the sign flag of the status register, and if it's a 0, we will jump to our new quarter-second label. And if not, we will write to the divide by 64 address instead and branch to the wait loop. So if we burn that to our ROM instead, we should see that it blinks a lot faster, and if we press and hold the button, it'll slow down again. Success! If you didn't know before, you now know how to make a 6502 based computer on a single breadboard featuring a 6507 CPU and a riot. I guess we'll call it a single breadboard computer. For now, I'm happy with a little computer on a breadboard, though it probably won't replace my other 6502 single board computer anytime soon. From here, there are literally millions of things to do with it. It'll easily bitbang SPI and I2C, which makes it super easy to hook up displays, keyboards, wireless modules, sensors, you name it. And of course, it's technically only a video chip away from practically being an Atari 2600. Leave me a comment if you have any cool ideas for what to do with it. My videos in the near future will most likely be about my old IBM XT motherboard that I'm slowly building into a working computer. I'll probably also play around with adding sound to my 6502 computer, and I might also make a video about an IBM P70 luggable that I recently partially restored. I'm also open to suggestions. Thanks for watching.